David, how are you doing? So David got a lead on this gentleman months ago. He's a patient. He's in the queue for, but he's got some cool stuff on digital FT8. And without further ado, you could take the floor. You can camp out right over here. Right here is fine. Well, that way the point where you got will be over. Boom. Right.
Great. Thanks, everybody. Yeah, my name is David. Call sign is K0B, and I'm really happy to be here. It's kind of been a little bit of a long journey. I couldn't make the last time that this is scheduled, but I really wanted to give this talk, and I've been talking about this with a number of members kind of over the last 2 years, kind of on and off, just working on an experimental state, what I'm going to show you. And so, yeah, title of my talk is Pushing FT8 Decoding Further. And what I hope that you can get out of this talk is a kind of very, minimal, like to know equations, understanding of all things that actually happen the FT8 decoding process, and understand some of the, smart design choices that went into this digital mode that has just exploded since its introduction in 2017. There's a lot of things that you can read on the internet about how to use it, but there's not as much, content on how it works under the hood. And then kind of at the other end of the talk, I'm going to get into some experiments where I'm trying to push FT8 decoding further. So that really means trying to detect even weaker signals and trying to make a more efficient. So when you run WHATX, if you want to use the full decoding settings, it's a mid-range kind of desktop computer. They recently introduced a version that uses multiple cores on your computer to try and do this decoding, and they're really trying to push that down there. But there's a lot of applications in amateur radio where you don't have desktop computer available or set up those types of things. So that's the kind of motivation to it. So with that, I will get into the talk. Actually, this is, will it do full screen? Yeah, I think this will work. Okay. All right. So yeah, a little bit about who I am. My name's David Crystal. Yeah, I was first licensed was an undergrad at the University of Minnesota. I was a physics and math major there, and I got my general ticket right away, or at least in the same session. And let's. Yeah, there's a lot of less things. Yeah, thanks. So let's see. Yeah, I was licensed in 2007. I was kind of active for a year or two, and then life got in the way, and I was inactive for a really long time. And then I decided I needed to get a hobby again, 2024, and decided to get back into radio. And it's kind of special being at this club because basically upgraded to extra, and I went to field day pretty much right away, and it was kind of mind blowing to see. So I don't think I'd ever operated a radio with like an amplifier before. We put up the giant Yagi antennas. Like all of this was and I really kind of liked it. And as I tell you more about who I am, you'll kind of get why I like all these things. So yeah, my background is I have a physics PhD, so I used to do experiments on experimental quantum computing, which seems very kind of out there or maybe not relevant. And I get to play with fun things like lasers, waves, do a lot of statistics and data analysis. And so amateur radio is kind of at least with these digital modes, it's a prime candidate for finding these weak signals and doing this kind of statistical analysis. And so my day job and career, now I work in kind of machine learning and data infrastructure, so big data processing. And so that ends up also tying into a little bit of the talk. As for amateur radio, it's kind of the wonder that any of it works, that you can just pick up a microphone. You don't actually need that much power, and you can contact people all over the world. And it just kind of works, and that you're literally just having your signals propagate through the ionosphere. Originally in 2007, in this theme of pushing stuff to the extreme, I stumbled on this video before I got my license, and it was something called a de-expedition, and it was BS7H, and it was to this place called Scarborough Reef, where they just built these little, like, pieces of wood on like a tiny rock on a little coral reef on the ocean. This is great. There's no monetary purpose. You're just doing it because you can, and so I loved it. And the same thing with the JT65. I kind of discovered that as a physics and math guy. It's like, all right, we're going to have 1 minute transmission basically to send like a few characters, and we're going to push that to the limit. And so that's part of me, why I'm here. So this I've been working on is like a library. I haven't released it yet because it's still kind of experimental, and I just called it FT8 lib. And it's intended to be like a library, and it's kind of a opportunity for me to learn the new programming language called Rust, which lets you write code that uses multiple cores in a safe way. It's really easy to make mistakes for humans when you're programming computers and using multiple cores. And Rust, one of the things it does is try to make that easy and kind of safe while still achieving really high performance. So I probably have about 15,000 contacts on FTA and probably a couple thousand on Slack. And this thing on the right here is the set of all the grid squares that I've worked, and a huge number of those contacts are on FTA. And so it really is kind of an amazing mode that you can work the world. And I love just kind of seeing all the great places you can get. It's been a geography lesson too. So what is it? It's at FT8. It looks simple. Every 15 seconds, somebody transmits and someone receives. You get a little message, and you're using an application like WSJTX on the right, and you just get a few of these decoded lines appear. But under the hood, the decoder is doing a lot of work, finding signals, estimating these bit confidence, repairing errors, and checking these CRC codes to detect if there's anything left. And then it does all these subtractions, and this is the simplified version of it. It's pretty complicated. And this FT8 lib thing is a Rust reimplementation of like the whole decoding chain. It's kind of refactored, and then it allows me also to understand what's going on and try and see if I can actually beat certain parts of it and kind of improve it, make it faster, kind of detect more signals. And so we want to recover more of these weak signals when we can kind of afford it on a desktop or something. And then we want to also just use less CPU. So we want FT8. Maybe you could have it even embedded in QRP. But it's just the software on it is since you're not going to get the best results. And so it's 15 seconds to transmit, but the actual transmission itself is like 12.64 seconds. So you have about 2.4 seconds to just do everything. Find all the signals, try all the things, decode everything, and send it, because you got to respond really fast. That's it kind of doesn't. That's even have ones, FT4. Somebody in Italy made FT2 recently. And so the other constraint is like, well, the extra decodes in this only count if the false decode rate is really, really low. Because generally when you see stuff in WSJTX, like 99% of the time, that's like a real decode. So if you get these false ones, it's kind of rare. So weak signal communication, amateur radio, there's like, I'm really interested in DXing. Like I said, it's been a kind of geography lesson. This thing on the right is a image of Andy Chadwick, 5Z4 BJ, located in Nairobi, Kenya. I saw that he was on. He's operating with 100 watts and a hex beam and a wire antenna. And I think he told me his noise level is like an S7 or something in Nairobi, where he lives. And even on his QRZ page, it says station is located in a city apartment with high intermittent as well. So he's other situations where you have weak transmitters and poor antennas, and you got to stay lightweight as POTA or SOTA activators. You want to use small radios, small wire antennas. People love to push the limit with QRP, see how far you can get on 5 watt, and especially from 12. anti-air HOAs, small lots, urban noise, indoor antennas, all these things are interfering with the hobby, and it makes it hard to get out on voice. And FT8 allows you to kind of get a little bit further, because it's definitely true. The old adage is like, if you can't hear them, you can't work them, and so that's why the sensitive thing is important. Now, FT8 people, it's, they're like, this isn't ham radio, or it's not as personal. I get it. It's more like a contest exchange. It's all business. You want to exchange call signs and grid squares, but I love looking people up on QRZ when I contact them on FT8. I try to find everybody in like all my squares. It's a fun thing. And this human element, this is a picture of, let's see if it comes through here. Oh, it's not loading. Oh, bummer. Oh, okay, okay, thanks. All right, well, there is going to be a picture that at some point will load, and it is, all right, there we go. I went to the Visalia DX convention, and I saw this guy there, and I recognized his call sign, and this is Andy in Kenya. I was like, oh my God, on FT8 in like December 2024, and 5 months later here, I'm just seeing you in person. So, gotta get good at memorizing call signs. Okay, so let's see. What is FT8? It's released in 2017 as part of CSJTX. It'll come in just a minute. It's a computer, and you're kind of emitting tones, and you're receiving these tones on your computer. It's created originally by a hand by the name of K1JT and his development team. And K1JT, his name is Joe Taylor. He won the Nobel Prize in Physics in 1993 for the first discovery of. So it's and his area specialty is radio astronomy. So he's pretty much just as famous in the world of amateur radio as he is probably in the world of physics. There's a number of modes that are in there, but FT8 is just one of them. It's created by Steve Frank, K9AN, and Joe Taylor. And that FT8 stands for Frank Taylor Design 8SK. It's frequency shift key. And it's so there are 8 tones or symbols, or what they're called in the kind of DSP world. It's very narrow bandwidth, so it's like 55 hertz. It can even be kind of narrower than CW. You're able to hear it a lot more faintly. On the scale of things, 25 hertz bandwidth. Single sideband might be 10 dB, 6 dB is your kind of minimum limit. Depends on operator skill. CW gets further down there, and then like FT8 is somewhere down to around like -20. So we're talking like orders of magnitude more sensitivity than sideband. And a lot of this, like I said, is optimized specifically. So these technologies are used in like your phone and other things. With this mode, there's certain design choices that are made for HF ionospheric propagation and the kind of realities of that, which involve Doppler spread, scatter, all sorts of things. This thing on the right is kind of what it looks like when you pull it up on your your radio. You can see these little peaks. This is about an average day on 20-meter FT8. And this is just in a 3 kilohertz bandwidth. So you probably have 60 to 80, maybe even more kind of conversations that are all simultaneously happening. And with the use sideband, it's a really efficient way to use the spectrum. And then the reason you see all the signals stop and start is because of that 15-second period. And then that little gap there, that's where you have to decode everything. So let's see. For this to come up. I talked about, the next slide is going to show like what a standard exchange looks like. It's kind of like contesting. You call CQ, you have your call sign, you give a grid square, somebody responds back with maybe their grid square. You could send, or you could send a signal report, and you get a signal report back, and you received it, and you give them a 73, and that's what it's kind of structured for. So there is a free text stuff, and there are some ways to do like contest exchanges and things like that, but it's very structured. And the reason that you want to do that is because when you kind of limit the amount of messages that you can have, be fewer and fewer bits. So you can send all this in like 77 bits. If you were going to send everything that you can send on a normal computer, it would be more like twice that. And so you're really trying to start from the beginning by just trying to be as efficient as possible in the way that you take the contact message and code it into bits. It's a really cool visualization from a ham VK3 PGO Pango Ray that he released open source, and this shows you like how does a CQ message even look. So it's CQ, KD0, BTO, and CM87 is my grid score. And there's 8 tones, and there are you can convert each tone into 3 binary bits, and then there's a kind of 77-bit payload, like I mentioned. And then I talked about these other things like error correction and CRC. So CRC is for detecting errors, and this error correction is for actually allowing you to play complementary but important roles. And so at the very beginning, there's these tones, this 3140652. These are called Costas tones. So it's just that same, it's a fixed sequence, and you play those 7 tones. It's in every single FT8 message, and it occurs beginning and the end. It doesn't carry any data. The purpose of like playing those tones is to allow you to like figure out like, does a signal even exist? And like if it exists, like can you kind of align to it and get find the right frequency and the time offset of it. So it's for the synchronization. And so everything's packed in there. 70 bits actual message. There's 14 bits for the CRC, and then there's another 83 that are used for error correction. So basically, more than half of the bits are not dedicated to the actual message itself. And so that's part of why this thing is so good kind of weak communications, because you can use that to recover and kind of fix things. And the total kind of transmission is 174 of these coded bits, and so then there's 79 tones, and I'll come back to that later. So it's frequency shift keying, and as I said, it's very narrow. So it's an example that you kind of this little. These are the sync tones, and if you kind of squint hard, you can actually kind of see that they play in the middle and at the end, and then it's the data that's in the begin or in the kind of middle parts. And so it's only 12.6 seconds, so you got 15 seconds, and there's that little gap at the end for the decoder. And then I do have, we do have some new hams, so I'm going to do this thing, and let's see if this works here. Oh, it doesn't play. It's going to play a. Oh, right. Yes. Let me see.
Just played it.
That's looks like it's not working, so I will. It's weird. It doesn't even come out of the speakers. All right. Well, it is a sound. So if you ever one time, you kind of just turn it down, unless you are kind of a glutton for that kind of. I don't know if I would call it pain. One is not so bad, but all right. So So now we're going to go in reverse. So I showed you how we encode it and then how we kind of transmit. And now we have to go in reverse. This is the like decoding phase. So you just start by just getting some 15-second audio recorded in the program, and then it goes through this kind of synchronous. It's going to try and find how many signals are there even in this band, and if they do exist, like what are their frequency and time offsets, because there's little differences in your clock, and you don't even know what frequency that it's going to be there, and you have to have an alignment of within maybe 10 milliseconds or 20 milliseconds alignment and time, and maybe like 2 hertz or so in frequency before things start to kind of degrade. So it has to be precise, and it's all got to happen fast. Then it goes into this phase where you want to take the tones that you hear, or actually kind of figure out what are the tones that you heard. So this is soft demodulation. The soft part of it means that, like, instead of just saying like I heard tone 3 and then I heard tone 1 and then I heard tone 2, I'm going to assign probabilities to those tones. And when you're at kind of the weakest level of detectability, telling the signal through way that kind of like statistical information. Then it undergoes this kind of error correction phase. You'll see these acronyms like LDPC, that's the type of code that's used, and then this BP and OSD, these are certain mechanisms that allow you to correct the errors with that type of code. And once it outputs something, completely know if it's correct. Like that stage will always output something, but it could be garbage. So you have the CRC check at the end, which allows you to kind of throw away and serve as a filter. And so that the only thing that you show to the operator is like a real decoded message, 99.8 times. And then there's a whole bunch of extra stuff that happens in WSJTX, but largely it will then take those really strong signals that it's decoded and then subtract them from the waveform, because you might have a really strong signal next to a really weak signal. And so, you saw that image earlier. It's like everybody's all transmitting on top of each other, but you can still pull out like codes that are from signals that are at least partially under much stronger interferes, because it does this subtraction process, and then it runs that whole thing again, and it can run it up to like 9 separate times. So it's really quite a computationally intense process as it exists today, and that's part of the challenge, like maybe efficient. I talked about those Costas array tones. And so remember, it's this fixed message. And if you look at like the shape of this, something that's kind of interesting is it kind of, it might look random to you, but there's actually a specific design goal with this, that if you shift kind of up or down or to the left, there's no symmetry. Like you're not going to accidentally have like one tone like kind of move backwards and start aligning with another tone. Like the only way that this thing aligns is when you're basically right on it. And so when you kind of sweep this pattern around and you're switching in frequency and time, and you're just trying to say like, where's the signal, where's this, you get a nice kind of dot where it's like a peak. And so this is like actual data where I zoomed in on a thing. You can see that it's within 0.8 to 1.0 seconds, and that it's at about 440 hertz. And so there's a few hertz coarse synchronization, and then there's some finer refinement that happens that I won't get into. So you're sliding around this thing, and you get this 2D surface, and that is what kind of allows you to pick out those little peaks, and those are all potential signals. If you look under the hood, the same meter that's used, all these little red dots through decodes that are like real signals that I decoded in some wave file where the band was reasonably crowded. And this is from about 200 hertz to 1400 or 1500 hertz. And if you can kind of look under these little red dots, you can see that the color kind of gets a little bit more intense. Some of them are to see the red dots are kind of on top of it. And that's of course what you would expect. And so, it all makes sense. You're finding real things. And then there's this kind of diffuse scattered stuff where it's a lot weaker because there's not actually any real signal there. So you're trying to figure out like, if this signal is real and it's not QRM, it's not like a birdie, it's not some other random thing. You just only want to test it on real signals. So it's kind of wasting time. And so the algorithm, it takes all these things. These are all called candidates because we don't know if there's anything there. And even if there is something there, we don't even know if we'll decode it because it might be just kind of noisy. So this synchronization step is developing kind of a list of candidates, and it's going to pass that down into these like later parts of the decode. So let's see. Like I said, it's a frequency shift keying modulation. So there are 8 tones, and you can index them 0 to 7. Now, when you looking at your Panda, you're seeing like the spectrum. It's like a Fourier transform representation of like the audio that you're hearing, and you can see the peaks come and go, and those are the tones that are there. If you're looking at it by eye and you saw a spectrum that looks something like this, you'd say, oh yeah, I'm super confident that it is tone 0. Like there's no ambiguity about it. There's like just a little bit of noise in there, but it looks perfect. There's no problem in saying it's tone 0. The challenging thing for weak signals is what happens when there's a lot of noise, and that can come from just pure atmospheric noise. It can be from interference that's sitting on top of you, and the spectrum is going to look more like what you see on the where true tone is a 0. And this is from like real band data, by the way. This isn't simulated. I just picked like a really good weak example. The true tone is a 0, but the true tone level is only about 1% or maybe 2% larger than tone 4, which is this other kind of band noise to be in the transmission. This is that SR of about -19 dB. So this is about 3 orders of magnitude weaker than like a sideband signal in terms of detectability. So we're really very close to the noise floor. So what you're doing when you demodulate is you are determining what the tone is that you think you heard at this particular time. But soft demodulation, you want to preserve this other information that, like, yeah, it was a 0, but like it also could have been a 4, or it also really could have been like a 5, maybe technically it could have been these other ones. There's some probability. You don't want to throw that information away because all of that is really valuable to let you know, um, when you're trying to do error correction, like, hey, this bit is really, really uncertain because it was, 2 different tones that it could have been. And so you want to preserve that information. And then just as a hint for the late part of the talk, estimating the probability of those bits is one of the kind of major results of one of my experiments. So trying to estimate, like, what were those exact bits at that exact tone time actually really matters, even for the error correction that's built and that works really well. So when you kind of convert this into binary, you go from these tones and then you go into these binary things. You might think like it's either 1 or a 0, and there's those 77 bits that I told you about. In the soft case, we represent it through something called the law of likelihood rate. Doesn't really matter what that is. You just have to know that, like, when it's a big positive number, it's more and more likely to be a 1, and when it's a really, really large negative number, it's more likely to be a 0. And when it's kind of in the middle, like basically at 0, you're kind of saying like it's 50-50. I don't know anything about it. I'm kind of similarly saying with that. And now I did promise that this talk basically doesn't have any equation. So I'm going to give you the gist of like what is error correction and how does it work in a kind of non-mathematical way, so that you can appreciate like what's going on under the hood without getting bogged down in kind of the math. So when you have kind of binary stuff, it's either a 0 or 1. Let's just pick 2 things. It's either a -1 or 1. We're going to say that that's the possible values of a thing that we could transmit on the air, and if or on the air. And if we have maybe 2 of them, this kind of 2-dimensional plot, it could be a -1, -1. It could be a +1, -1. It could be a -1, 1, or and 1, 1. So those are the 4 kind of valid values. And you can note that the kind of distance between these, you kind of divide by 2, but it is exactly like 2. And so the distance between these is always like 2, or it's kind of greater. So in this case, if you're going from the lower left to the upper right, it would be square root of 2 times that. So it's like a little bit larger. When you have really good signal, so kind of what they are. You don't really need to do any error correction. So your transmitted signal, which is represented by this kind of red circle, is kind of your uncertainty about how, like, what the actual bit value is. You can see that the red circle pretty much lines with one of the dots. There's no problem about telling you what it is. When you use an error correction code, you're kind of trading off. Like, I can't use as many bits for information, but what I'm going to try and do is make the distance between these 2 or these points that I do allow at valid values, try and make that distance larger. And the larger and larger the distance is, that kind of better the error correction can work. And the way to think about it is like, if this yellow circle here represents your like really noisy value, you don't know which tone it is, and you convert it into this binary thing. It's kind of wide, and it's basically just on the border of this threshold here. And in this case, with error correction, we're only going to allow specific values like -1, -1, and +1, +1. So we don't allow these to be valid values. And you can actually see that if we just did the kind of obvious thing, picking whatever's closest, for this value, and we allowed like this lower right value, this thing would kind of, zap right over to here. You'd think, oh, it's this lower right bit value, but that one's not valid in this kind of world of codes that I'm constructing with error correction. And what you find that because it's just a little bit, in this case, below this decision line, it's going to be kind of, this one is the closest one, and that is the correct code word in this case. And so all these error correction algorithms like BP or OSD, these kind of abbreviations you see, all they're trying to do is just figure out like, okay, given the yellow dot, which one of the black dots is the closest. So that's it. It turns out like when you have a lot of bits, this is computationally like a high dimensional problem with lots and lots of common 2 to the 7 power, something like that. So you just want to think that it's the closest dot. And that's basically what error correction is. So anyway, no math. FT8, it uses this thing called a low density parity check code. It was first conceived in the 60s by a guy named Robert Gallagher at MIT. They had decoders, but there were no computers that were to run. And so they kind of fell out of favor and were like forgotten. There were other things that took over in the 80s, 70s, that type of thing. They were kind of rediscovered in the 90s for 2 different reasons. The one is that we finally had computers fast enough. 2, there was that these codes that can actually get really, really close to what's called the Shannon limit. So that's like the best that you can do. That, like, there's no possible way to design any error correcting code that's better than achieving this like Shannon limit. And these LDPC ones turned out to be really good for that. And then in a fun story, which some of them may laugh at, and patents were a mode for choosing LDPC. There were these things called turbo codes that were really, really popular. They had all these very, very fancy algorithms. All that stuff was patented. And so it's like, all right, well, we have this LDPC stuff that's been around for a long time, no patents, and it's basically just as good. So these methods, like I mentioned, propagation or order statistic decoders, these are just kind of a lighter, faster decoder, and OSD is like maybe a deeper, more computationally intense one. But it's not really super important how they work. And then CRC is this cyclic redundancy check that I kind of mentioned about there, and like, okay, things spitting out, even press. Okay, so now I'm going to get into the actual kind of results of this like library thing that I've been working on for a while, just on and off. So one of the things that you can do or think about is like, hey, if I want to try and detect more signals, these coders have parameters like how many they try to around before they give up, and that's kind of called like the depth. But as you increase the depth, it takes longer and longer and longer. And so on this plot here, you have the signal to noise ratio. I'm sorry about the size of the pix. It's like 27 decibels signal to noise down here, negative 24 down here. So we're really at kind of the limit. And then this on the left is the average decode time in milliseconds. So it's about 1 millisecond here, and then it's about 1 microsecond here. So that's 1 millionth of a second. And then let's see, at 10 to the 2, it's like 0.1 seconds, so 10th of a second, very tough. And the things that I want to show you are these 2 things in gray here are the kind of existing decoders that are in WSJTX. It's one of them is this belief propagation, and the other one is this order statistics decoder. And I like to really fast code and use advanced tricks on computers, and advantage of these special instructions or ways to do binary computations really fast. And so I wanted to write a really, really fast implementation of both of these. And so basically this version that I wrote of OSD is around 12.5 times faster. So it's around 100 microseconds instead of a second to a decode. And then this belief propagation version that I wrote is about 3 times faster. So it's about 60 microseconds. So besides like just re-implementing what exists and making it faster, that's already nice, because it means like literally if you can just do things faster, it's better. You can run on a weaker computer, or you can time, more things to get sensitive decode. That's what this curve that you kind of see from the upper left to the bottom, that's your kind of limit. If you want it really fast, well, then you're not going to be as sensitive. If you want it really sensitive, well, then you got to spend extra computer time. But the more you can put on to the left, the better that pretty much is for making this work on all sorts of devices. I also wrote some new kind of state-of-the-art like published in academic papers approaches. And it was interesting. I found that they weren't actually better in this kind of mid signal to noise regime. I thought, oh gosh, 2021 and the thing that the WST came out in 2007, surely it's got to be better. And it's like, no, the 2007 one had some really clever kind of math. And so having put all that effort into making that new implementation, then having to think like, huh, why didn't this work? Was a really educational to figure that out. But turns out that at these kind of super weakest levels, you're getting a couple dB across this thing, that it actually does end up being kind of the most efficient thing. So for a given sensitivity, it can decode, the fastest, if that means. So this PBOSD decoder order 3 at the same PBOSD decoder at order 4, where you're getting down to almost like -27. And I think like the Shannon limit is like -27.2 or something for FT8 with this S. So you're pretty much all the way there if you're using the and the other thing that's kind of interesting is I wrote another implementation of a kind of approximation to belief propagation. So it's called fast min sum. And that'll do a decode in just 1 microsecond. So you're coming down, the fastest you get in WSG was around 186, like for that, original implementation, 186 microseconds. Well, here you can at least attempt it in 1 microsecond. And again, so you don't have to just pick one. The whole thing can kind of mix and match. So what you really want to do, and there's a lot of stuff already in WSJTX where they're very clever about kind of scheduling this. You want to take all your high and R stuff and just use this fast as possible, and then take all of those and then subtract those decoded messages, and it's going to reveal the weakest ones, and you kind of save these other, more intense methods for those weaker signals. Yeah. Sure. Yep. Yeah. Yes. Yes, that's the point. But I need to quantify this carefully for the oh yeah. Sorry, yeah, thank you for the reminder. The question is, when I say sensitive, does that mean you're seeing more decode in WSTX? So I have to be really careful about how I say this, because there's 9 different layers of subtraction that are in there, and these decoders are just one part of it. And the experiments and data that I'm showing you here, I'm showing you mostly the speed and stuff right here, but there's technical question of like, well, you did these subtractions and then you tried maybe these weaker algorithms, would you maybe get lucky and find something? Maybe. But generally, like, yes, like this thing kind of shows it. Like if you are using these, so this purple line is the deep decode that WSGX uses. It's kind of normal configuration. It does have like kind of analogs of this, but they're never used because they take really, really long time. But with these newer kind of implementations, you can squeeze out this last, kind of, I don't know, 0.8 dB or 1 dB of that would be the goal. It's like that. Just take this, put this into WSGTX, and literally every single thing will have at least a better chance of decoding, something that you wouldn't see. Yeah, another question?
You want to mic?
There you go.
Yeah, so I'm just curious about the other metrics, because the decode metric is great for decoding, but then you're also looking at subtraction, right? And so you need presumably time and frequency alignment as part of that. So do the metrics align? Like if you're doing a good fast decoder, does that get you the other metrics you need at the same time?
Yeah. So the way it works under the hood is when you could keep everything else like fixed in it. Is like you could just replace this decode method. And when WSX finds a decode, now you have the advantage of like, oh, I actually know the complete waveform, like not just the the fixed tones that are played there. I know the complete waveform, and it does like a little bit of refinement to get very, very close. So you would have the same subtraction, like nothing about that changes by using this decoder algorithm. It's just like one chunk of it, and it's only doing that error correction. You just have a higher chance of getting that message, and so a higher chance of then subtracting it when you otherwise wouldn't. And so it is a complicated thing, but this is kind of the way to at least kind of compare them. Does that answer your question?
Another question.
Sure.
On the previous slide, on the lower left, the words are cut off. Could you,
Oh,
Leave it.
oh, yes, they are. Oh, bummer. Okay, so that was that was the point I was trying to make on that one is that like you're not limited to just using one of these, and GTX doesn't use one either. It kind of switches off and you know, tries to use faster ones and then slower ones, kind of like how I was saying, where you if you know, you kind of know what the signal to noise ratio is, you can estimate it beforehand, and so you can just use the fast decoders on all of that and then subtract all of that, and then kind of save compute time for these more advanced methods on the signals that don't decode or are the weakest ones.
is that done in real time, those decisions? And
Yes,
Okay.
yes, yeah, you can do that in real time.
Okay.
And there's a thing I have that does a interesting kind of related estimation later in the talk.
that's the first one is on next graph. Good.
Yeah, I gotta
Sorry.
explain actually what this is. I remember I didn't tell you what the y axis was.
Okay, so I have old eye syndrome. Could you
Yep.
just summarize from left to right? You have, I think it's 5 curve there.
Yep.
Could you just summarize what each of the curves corresponds to?
Yep, I can do that. All right, so the I'm gonna do the axis first. So here you're at like negative 21 dB SNR, negative 22, 23, 24, all the way down to about negative 28. And so this is like if I take a perfect sequence of bit, and then I add what's called additive Whitehouse noise. So these are simulations, although later I'll show you the real data stuff. And if you add a little bit of noise, you know what the signal to noise is then in this kind of FT8 normalized scale. So I can add progressively more and more noise. Or really what happens is you just make this weaker and weaker and weaker. It doesn't really matter. And so as the signal to noise ratio gets lower and lower and lower, on the y-axis, we have the decode probability. So given that noisy input, what's the chances that you decode it? It's 0 down here, it's 100% here, and here's the 50% mark. And so it kind of makes sense to compare, well, where's the 50% for these different decoders? And now there are, yeah, let's see, there's actually 7 curves here, but they overlay. And the reason is because it's just showing that the Rust and Fortran agree exactly. This brown curve is that fast min sum, so it's almost as good as leaf propagation. It's hugely faster. And then the red one is this kind of belief propagation, and the Fortran and the Rust are identical because, or yeah, they're basically the same algorithm. And same thing with the purple one, that's that order statistics decoder. And then this green and this kind of orange color are this PB OSD, so it's probability or it's newer one. Wasn't it's newer, but it only works best at this lower range. Yeah, I got another question.
Thank you. Very interesting. So for the benchmarking, I agree with you. White Gaussian is perfect.
Yep.
But what we have is fading. It's like a wonder. So it means slowly your CR, it goes away.
Yep.
You still have the 3 repetitive patterns that you can sync.
Mhm.
Have you, in high-speed digital, they use MLSD and DFE. So have you used that or tried to implement that? Not what you're using here is very interesting, but not help is wonder. So slow fading, very
Yes.
slow.
So actually, a little later in the talk, what I'm going to show you is remember how I was saying that estimating like the bits of the tones was really important, and if you can just be more accurate in those relative bars, that would get you on more decode. That would be the best place. This is when you're only looking at the data payload, because that's the only thing that is encoded with LDPC, not the sync symbols. So we'll get to I think something that'll be more interesting on that axis a little bit later. It's a nice result. It's not going to be what you're super excited about. This is result number 2, which is kind of machine learning based filtering of unpromising candidates. So remember, we go through the sync thing, we get this whole list of candidates. Well, it turns out that like WSJTX has a heuristic in it. It's like if the sync symbols don't quite, match up, if the SMR is really low, if there's kind of disagreements in the parity check, like this thing is probably never going to decode because it's just that bad. There's too many things, but this is a heuristic. We come up with these little rules and we try and say like, all right, if it's worse than this and this is this thing and this is this other thing, we're just going to throw it out. And then that way we don't even have to do all this expensive stuff. So the way to the amount of computation that you need to do. So that LDPC decoding, it is really computationally intense. So there's a question, okay, can we use machine learning maybe to make a better kind of rule or a better what's called classifier? The technical term would be a binary classifier that would predict, all right, I don't know what message is. I can look at sync symbols. I can look at a few parity check disagreement. I can look at a number of other kind of things. These would be called features or inputs to a machine learning model. And I would want to train that to predict on a scale between 0 and 1, what is the chance that I can actually decode this thing? Because if I can predict the ones that I will decode and the ones that I'm definitely not going to decode, I'm just going to throw all of those and I want to do any more work. We don't have to go into the details on this machine learning algorithm that I chose to do this. I'm happy to answer questions about it for people who are kind of interested in it, but it is a algorithm that is called XGBoost is the package. It uses boosted decision trees. And you can think of those little rules, that heuristic, like if the signal to noise is above this, and if the number of sync symbols disagreeing is below this, those are like decisions, and that is like a tree. And what you try to do in this boosted decision tree algorithms, you have a machine try to construct trees of decisions that kind of split things out. And that's kind of it's kind of an okay thing if you just grow one tree. Like you can only get so deep and you can only segment it out, and you really want like a nice perfect segmentation as much as possible. And so what this technique does is it actually kind of adds like little weights to each trees and then kind of adds them together. And then ultimately you're just outputting a number between 0 and 1. And then the hope is like this thing develops like a nice thing that separates away a lot of the kind of things that will decode versus that they don't decode. So let me, yeah, sorry again about the small text on these. So this plot is the recall of things that will decode. So I basically turn off the heuristics in WSJTX, run it all through the decoder, and find everything that's like a proper decode on the other end. And then I turn the heuristic back on, and it's this JT9 gate. But their heuristic back on, and it says, oh, it's 89.96 recall. Recall is the kind of fraction of things that we let through that would have resulted in a real decode. So that's really good. So the heuristic in WSJTX doesn't drop any like things that are going to really decode, because those are the things you don't want to lose. It's really, really high. And it only lets 20% these like things we call candidates in the case. So it's already doing a great job at filtering out pretty much 80% of all of that stuff. But can we do better? So with this tree boosted algorithm, like I said, there's like it outputs scores between 0 and 1. And you can kind of just say, all right, well, everything below, 0.7, I'm going to throw that away. Everything below 0.9, you can pick wherever be, and that will trace out this curve. And as you become more and more aggressive at cutting out these, decodes, you're actually starting to lose recall. So here you'd be cutting out 40%, because now you're only at 60%. You'd be cutting out 40% of things that are going to need to recode. So you definitely want to be there. But hey, you're only admitting like 5%, and relative to 20, that's a decrease of 75%. The important thing to look at is this little red dot here, or potentially this green one. With this machine learning model, I can operate at about 11.8% admitted through, and it basically like you don't any cuts. So 11.5 or 11.85 versus 20.2 is about 41% fewer candidates, and so that's 41% less compute that you would have to do for that computation. Now LDPC is only maybe a third or so, like the total thing, it's cutting off 40% of a third of the total thing, but every little bit kind of counts here. And you can even go down to like 10% and you're still at like 99.8 kind of recall. And so you're making kind of a better filter to cut out those kind of unpromising things. And that way you save yourself what you don't have to do. We're going to get into like an actual experimental results. So now I showed you earlier on the decoders, those are simulation results. The XGBoost ones, that was actually real data. So I didn't mention this, but I have like 100 gigabytes of wave file just on an FT8 set on a hard drive at home. So I think I had over 2,000 wave files. That's what was used to transmit that. So that XGBoost thing that you saw, that was on real actual data that I think is quite representative of real conditions. So it has the fading, it has the Doppler shift, all that other stuff. kind of baked into that. And now I'm going to go into kind of the third, which is trying to estimate those like bits better, those like ratios that I talked about. And so let's see. The question that I had for this experiment is, if we take the same kind of candidates that we've held out, that's what this kind of gray box is. Sorry for the small text. These are these candidates. Don't change anything about the kind of decoding that WSJTX does on its first pass, because the subtraction and all this other stuff, it just adds in so much complication. You want to kind of just say, all right, let's, instead of trying to replicate the whole like 9 layers, and I think you could potentially try LDPC like over 100 times on its WSJTX, and how it works. Let's just do a single straight through shot, and let's compare these two methods of estimating those probabilistic like bits, those binary bits, those like LLRs, those plus and minus numbers. So WSJTX, it has some really good formula for estimating what the log ratios are depending on the tones. I mean, you're basically just trying to say, what is it, tone 0 or tone 7 or whatever, and convert that into binary and do the math in the right way that it kind of works out and you don't lose any information from that. We're going to have an alternative method we'll talk about in a moment. We're going to just kind of switch these out. So we're going to just keep everything the same candidates, the same error correction, the same CRC, and then we're going to compare the decodes at the end, and we're going to see what we get. And then the label set, what we're going to use for this is we're going to just let JTX, which is, or WSJTX, which is best decode out there, let it run its whole multi-pass thing and get every single. So we're going to say, all right, that thing ran like 9 subtraction passes up to, its deep. We just operate it in its deepest mode. What's everything that we get out? And now we're going to compare the existing formulas with this alternative method that I'm going to tell you about on just a single shot, and say, in one shot of how fraction of everything that we know exists did we even get? And then the kind of inference or expectation is that you spend a lot of time getting this to actually work, and then you could put it in the real WSJTX, and then you'll start decoding things that you didn't even, that WSJTX doesn't even decode, which I haven't gotten to that yet. So that's why I'm trying to speak. It's it's experiment. I've tried a lot of things in this library. I've tried a lot of things that I'm not including in this talk that haven't worked, and so I'm just trying to be careful about it. But this is what I think is the most exciting personally. Okay, so can we design an LR calculation? Also, then a function, and you just get out some numbers. So it doesn't really matter what that function is at the end of the day. You just want to get the thing that estimates the bit ratios the best. And so this approach that I chose is to try to design several different neural network architectures to try to predict the log ratios of those 174 bits more accurately than the kind of formulas that are in WSJTX. So we're not going to go too much into like neural networks. They can kind of be complicated. It's a sequence of, multiplications of a weight with a kind of input, and then it kind of adds together with weights, and they have different connectivity and their style of architectures that are there. But at the end of the day, they're kind of a function. You're trying to take in, noisy data and then output whatever the best estimate is for these, bits. So this thing takes the raw like spectrogram. Once we've found a signal, we've like it by this cost, this candidate, we find frequency and time as best we can within a little bit of error. Then we take the 79 tones. So there's these 79, fast Fourier transforms, and those output a complex number, and that encodes kind of the amplitude of the signal and the phase. So that's what you represent. I kind of transform that into a phase invariant form, because the phase itself is the absolute phase is meaningless. You don't know the phase ahead of time. That's part of also why FT8 works, is you don't need to have some crazy synchronization with the person that you're trying to communicate with. So up to a global phase, it's irrelevant, whatever the phase. The only relative phase between the symbols matters. And so you kind of convert it into that form ahead of time, because that's what the neural network needs to focus on. It's going to create these 79 kind of symbols or tokens. So I chose to use a couple different architectures, but the one that I'm at least describing at a high level is called the transformer. This thing would appear in language models. It appears in all sorts of cases where you have a sequence of items. It's like, you know, item 1, then item 2, then item 3, then item 4, and they occur in kind of a sequence together. And it's like, well, that's kind of natural for these tones. You know, there's the first tone you play, the third tone, et cetera, et cetera. And the idea is that we're not actually even using just the spectrum of the actual 8 tones where we like expect them to be. You can use, you know, what kind of information is in, you know, to the left or to the right of that. That can give you information about the noise. And the other, like, instead of trying to like figure out the bit or symbols like one, you're actually trying to estimate all 79 symbols or all 174 bits simultaneously in like one mathematical operation. And there are things like fading or Doppler shift or all sorts of things, or even that your sync is like a little bit off. And every time that you kind of deviate on one of these things, the formula can kind of get a little bit less accurate. But a neural network has the potential to kind of learn, like maybe it can kind of detect that like your sync is like a little bit off, and it will adjust for that kind of automatically because it's seeing a lot of real data. And that's the kind of other part about this is you run it here where it's the raw data, and then it puts it into these symbols and it gets you to these bit values, and then you have these all these decoded, you know, things, so you know what the true value is, because I have, you know, 200 gigabytes of wave files, and I think, you know, training data for this is like 90 gigabytes. I can't even remember. It's at least 2,000 wave files on this. I think it's substantially more that went into kind of training network. I use the training. What that means is there's there's all sorts of free parameters, just little floating point numbers that could be anything. And they're actually, you know, they don't really have a particular interpretation a lot of time. And you're trying to find the right set of little floating point numbers that give you the best performance. And so you need to deal data and kind of keep toying with these numbers in a kind of intelligent way until you get one that does a good prediction. And that's what, you know, essentially training a machine learning model or a neural network ultimately kind of is at the end of the day. Okay, so this is I think what is the most kind of exciting result of all the stuff that I'm showing you. So this is not just like a computational speed up. That's what I focused on more. And then, you know, I talked like, oh, you know, these decoders are a little bit better. This is just using the same decoder that's in WSJTX. And what we're going to show on the left of this plot here is the number of true positive decodes, and then it's to noise in dB bottom, and I've binned it. So that's all the, you know, decodes that existed between -30 and -20 are in one bin. You can see there's barely any there. -20 and -15 are in this bin, and so we're going to compare, you know, some methods there. And -15 to 10, -10 to 5, 5 to 0, and 0 to 10. And stuff, but it's not worth because it's, you know, basically perfect noise. The reason you see the shape here is because, like, in the real wave data, like the actual band conditions, like all these wave files that I'm talking about, this is where most of the signal to noise ratios are that are reported on my machine when I'm recording it. So between, you know, around -20 and maybe up to 10, and then, you know, it's only somebody who's got a really big antenna and they're in, like, I don't know, Los Gatos or Mountain View or something, and it's like, all right, you get a, you know, plus 38 on there, and it's like, I still call them on WSJTX if I want to make that contact. So if you hear me and you're thinking, oh my God, this is a mode for DXing, why is this guy in CM87 calling me? I just like, it's like saying hello. So you see a lot of signals, decodes are in there, and in this data set, there's around 8,000 decodes. Is the level here. So in this kind of signal to noise bin, that's what it is. And then these kind of colors here, these light like blue ones here that all actually are kind of bottom. Those are the kind of formulas that are in WSJTX. So if you take those formulas and then you put them through the same decoder, then you get out a certain number of decodes. And this is in that single shot kind of thing. So we're not doing subtraction. We're just comparing them kind of apples to apples in one shot. And when you have these various neural architectures, the yellow, orange, the red, or this purple, you can see that you end up getting like more decodes in these bins in a single shot. And so then if you kind of, this is kind of hard to see, because what you want to know is like, well, what's the relative percentage that this is getting relative to like how many decodes were even in that bin? Like maybe there weren't that many there, and so this is decoded 100%, or maybe there were, this is only decoded 20%. How do you know? Well, you want to kind of normalize it, and that's what this plot on the right is. So it's the same signal to noise bins, and then now it's the recall. So that's the number of like true positive decodes divided by the total, and the total is like, again, just like WHATA, as deep as possible. So you're going like, I don't know, recall like 5% or 7% to like 40% with this transformer neural network architecture. Just for the sake of mentioning it, I mean, I tried some other architectures. This multi-layer perceptron, that's like a very classic one that has a long history. There's this convolutional neural network. They patch of pixels, and they're very popular on a computer vision applications. So for kind of identifying, what things are, or images, it's really popular to work with that. And they're popular because they can kind of use like neighboring information. Well, the way to think about it in FT8 is like, you want to use like this, not just from one symbol time period, but from the previous one and the one after and the one, maybe two before or two after. So because maybe there was a noise spike that happened there, or maybe it tells you something about the fading, or maybe it tells you something about the interference pattern that, because somebody was stepping on top of you. There's a whole experiments that are trying to figure out why it works in the way that they do, but it turns out the transformer one is better. So if you do the total kind of comparison, like the best one of any of the handcrafted methods on this data set was around 25,266 decodes in a single shot. And then the transformer is around 31,000 decodes. It's an increase of 23% more decodes you would get in using this in a single shot compared to what exists in WSJTX. And now these formula things, these have been like tuned. They put a lot of, I think, thought into, and it's actually really cool how they work, but they can't really adapt to, fading, or they can't really, can't really adapt to, frequency. There's all these little things that can happen in the real world signals. And at least with neural networks, you might be able to kind of learn a function that can kind of automatically cancel that stuff out. So that's a hand wavy version, because it's hard to understand what these things do, of why this actually works, potentially better. What was in the ends here, that's the biggest kind of jumps, which is that like very weak signal regime. So in the -30 to -20, you're getting like 10% recall. With the formula, you're getting 40% recall. So that's like 4 times as many. In the second weakest bin, the -20 to -15 range, you're getting like, 39%, when you put like 66%. So it's, less than effect 2. So that's really exciting. And it's part of the reason is probably that it's using the context of the whole thing to kind of hopefully counteract fading or interference, or like slight errors in the timing and frequency offsets there. Okay, so thank you for bearing with me on that really technical, a lot of words being thrown at you at a very high rate talk. So I'll move to the conclusions. So ultimately, like, this talk is, oh yes, we got a question. Great.
I have some questions here.
So just kind of a quick question about the difference between real life and sort of theory. What would optimal if you did have Gaussian white noise for interferences? Do you have a sense for like how close we're getting with these much more real world noise properties?
So I got to think about how to answer that question. So the formula-based methods in SGTX are quite close to optimal, assuming like the additive white Gaussian noise, and assuming that the phase coherence of the signal is perfect. Meaning, technically I've said, oh, FT8, it's FSK. They have a little modification. The phase, it doesn't just jump when you change between tones. They keep the phase continuous, and because they keep that phase continuous, that the knowing one symbol actually gives you a little bit of information about the neighboring symbol behind it. And so I'm going to live into neural network or whatever, but it's kind of an inside baseball thing. So under that level, they already do a lot to achieve like pretty much the best. So they use this, it's called like non-coherent block demodulation, and it's a paper in like 1993 where they're basically like continuous phase FSK and the intervals. That's exactly what an FFT gives you. And they even had a nice fun choice, the designers of FT8, where the math works out very simply. And I'm like wondering, was that intentional? And so you get the exact receiver out of the FFT coefficients, and then they do come between, it's like n=1, n=2, n=3. So it'll take advantage of the phase for 3 symbols. There's an experiment that I did where that I didn't show. It's to put all of these symbols on something called a trellis, and you can kind of propagate phase knowledge across all of the symbols. Like, why limit yourself to just 3? Because then you have to do 3 all in a block. The problem is with that analytical method that they're using, the complexity blows up with n. You go from, you have to do like 512 different combinations with n equals 3, and then you have to do, 1096 if you're at 4, and it just isn't worth it anymore. But anyway, so they're really, really close. I would say, if you're assuming everything is kind of perfect. So.
Yeah, I had a question here. Okay. And Ben, if you can let Zoom know if they want questions to start texting away. Oh, got a question up here.
Yep.
You didn't say anything about the computational cost of all these ML based.
Yeah, actually, that's a really good point. I didn't say that. So I do think on that, the time it takes to do the log likelihood ratio in that transformer model, I haven't optimized it yet. It's about 100 microseconds. So that's doable, especially if kind of like how I said, you can fiddle around and use the really cheap decoders for the strong ones. Well, you can also do the same thing with the LLR formulas, like use the fast form, like all the like easy one, and only come back later and do the more intense one. So it's about 100 microseconds, but that's actually about the time that it takes to do the LDPC anyway. So it'll add to it for sure, but very good point.
When you say that something takes, say, 100 microseconds, is that normalized for you doing this all on one platform with one implementation?
Yes. So this is okay. So yeah, these are all of these numbers that I'm giving you are on my like Apple Silicon M3 Max thing. So that like it's all at least relatively correct. And that, for what I'm trying to do, it's like you're just trying to make it faster and faster, but it should translate. There's nothing particularly special about it. Maybe some embedded devices it would be a little weird. But yeah.
It seems to me you have a bootstrap opportunity because you're training your machine learning only on things that were already successfully decoded.
Yes, question. So that is kind of the next. It's like, how do you know what actual signals were there if you're just given a wave file and all you have is the best kind of decoder, which is WSJTX. So if you've developed a method like this, the question is, well, don't have a bootstrap opportunity. And it's like, yeah, the phase here, like, all right, get this to work as well as possible on the single shot. And then once I've done that, I'm going to start doing this like subtraction stuff and try and see like, okay, now I'm going to actually approach the complete recovery of everything that WSJTX gets. And the big question is like, how far will you go to that question? I don't think it will be the full 23%. I think it will be that 40% in that weakest signal thing, because again, that subtraction really does play a role. And maybe we're just, using this fancy neural network and it's kind of getting stuff that WSJTX would have gotten if you had done signal subtraction. So that is the big open question, but the kind of way it's like make this thing as good as possible and then thread it through the whole thing, do the whole subtraction. And then that's exactly it, is you get those weak decodes that you never saw before. And then you could put those back into your training set, which is kind of what you were saying. And then it's kind of a flywheel is the appropriate term for how people like to refer to the process.
Question? Okay. Oh, you got another question?
Okay, well, first, thank you for your presentation. You started out mentioning that 2 of your goals were greater performance, as I understand, to enable FT8 to do a better job of what it was designed to do. The second goal was to enable doing some of these things, or all of what FT8 does, on lower power computer platforms. You can put it in a backpack, for example. So it seems to me some of the things you mentioned cannot do both of those at the same time. So could you just, from a very high level review, which of the techniques you're proposing or you've designed accommodates one of those versus the other, or even both?
Yeah, and yeah, the question, and part of it is that it's a trade-off. A lot of what I focused on, like initially with those like decoders, is just making them faster, or coming up with one that's even faster. And so it, in every case where you'd want to operate it on a weak CPU, the thing that's it's going to benefit you. Like the order statistic decoder is usually the one that is not implemented in like other libraries of FT8 that you can find on the internet. They usually only implement that belief propagation because it's fast and it's easier to program too. The OSD one is just kind of more complicated, and especially with like that stuff, it's just not worth it. So, yeah, it's a really complicated question because everything depends on everything else. But I'll try to put it simply. So, if you have that fast min sum decoder, I mean that you can get a microsecond decode in that, and so all of the easy stuff on a low power device, like actually that's thing people make like hardware decoder PC. That's like the first thing that they try is this like approximation to belief propagation that works on like with just like binary, and it tries to avoid some of the floating point stuff. That would improve performance. I think taking even the regular belief propagation, making that 3 times faster, that'll improve it. The order-statistic decoding, making that 10 times faster. That one I'm almost like, can it really be that much faster? I mean, I wrote it pretty well. I spent a lot of time optimizing it, but that was like over 10x. And so it's kind of a hard to answer question because it depends on like, well, how low power is that speed? Like maybe it's low powered, you're still not going to be able to do it even with that kind of speed up. I do think that XG boost thing where I did the pre-filtering where you cut out 20% of the stuff that comes out of the sync phase that goes into the decoders with existing WSJTX, and then 10%, that definitely, no matter what environment you're on, that ML algorithm, the tree algorithm there, one of the greatest reasons that you use such an algorithm is it's really fast, and you can also kind of construct like simpler rules based off of it. So maybe you could build the machine learning model, and then you're inside of those trees and try and extract actual heuristics from them and construct like a formula, and then there's no like fancy ML model at all. And then the transformer one is kind of interesting because I think it's going to be the hardest to run on anything that's low power. I'm going to try and make it like the fastest CPU implementation possible. Like I didn't use a GPU, by the way, for any of that. It's all CPU. It's and so that one is going to be the hardest thing to run. But on the other hand, like it's in a single shot, so you only have to run it once, and you're not doing these like 9 rounds of subtraction. So maybe you could actually make it make sense on a weaker CPU, even though that is like the kind of computationally most intense approach. But I don't know. It depends on like what is it going to be when you put all the layers of subtraction in there, and then you just got to kind of try it out and see. So they all kind of affect the ability to do things on low power.
I got a question back here, and then I'll get Mark there. You said you were doing all this in Rust.
Yep.
Which makes sense because several reasons why that makes sense. Less memory usage, but also much faster. Typically, the numbers are like about 40%, depending upon what you're doing. I can see even the weaker computers also come with multi-core. With Rust, you have async. And so having said all that, how long did it take you to actually learn and do this in Rust? Because that's not an easy language.
Well, that's part of why it took like 2 years, and I learned a lot of things. I did a lot of I thought where I was real poor, and then it turns out now the authors of this thing made some really clever approximations. Like they know their stuff. I mean, that's of course what you'd expect. So, I mean, it's like 2 years on and off. There were periods of time where 6 months I didn't do anything. But the intent is that this is just going to source at some point. It's kind of in a state where it's a lot of experimental stuff that's like onto it. And you wouldn't need to know Rust in order to use it. I think that's another good point that I want to make. The dream of this would be you publish this Rust library, and it's just a function that can be called. It uses the C like API, so you can form call, or if you're in C or writing, you can just call this function in this Rust library, and it doesn't really matter how it works. It doesn't really matter what language it was written in. And so that would be the dream, is you could put it in WSJTX, and you don't have to change out, you don't have to rewrite every Rust. I mean, uh, the a lot of the DSP code in WSGX is written in Fortran, which is kind of, makes it limited. It's harder to kind of hook it in as libraries to other programs. So I think that at least Rust, it has a lot of ways that it can target other things and you hook it into many things.
Good, thanks. Yeah, Rust is writing for the compiler before you write for the actual program.
Yep.
Okay.
Battling it, for sure.
Okay. Tony had a question here.
Just sort of actually sparked by the bootstrap comment. I'm sort of curious if you've done any, synthetic data generation using your actual WAV file so you can push your
Good idea.
SNR wherever you
Great
want.
idea. Yes, it's perfect. So there's opportunity generating synthetically. So I think what I would do is I wouldn't generate the waveforms and the noise like purely synthetically. I don't think that's like going to be interesting. Yeah, exactly. You're like training it on like the perfect thing. Unless maybe there was some element of like the phase space, but because all bits kind of or zeros and ones in there. The thing that I think is really interesting is making it more robust to like slight frequency and time offsets. Like that synchronization part, it gets close and it's, within 20 milliseconds. But I kind of told you like, yeah, if you get too far away from that, like it starts to die. What data generation would be the waveforms that you have, you just artificially insert like little shifts in the frequency and time in it, and you make like maybe 6 copies where you're kind of randomly shuffling it around and then train it. I think that's absolutely the way to do it before releasing this. So that's already in my backlog, but I haven't actually done that yet.
I think I got a question here. Pretty soon we're gonna have to wrap it up. Uh-oh, gotta make them quick. Okay. You, Connie, Justin. Okay.
Yeah, hi, David. One question about your training data. You said you had this collection of WAV files, and you'd mentioned recording them. Are they all things you recorded yourself, or did you try to source off of equipment and locations?
Yeah. Also, and so I sort of wonder about this. It's like, oh, well, I probably hear, mostly US call signs, or I probably, I'm not going to hear a lot of stuff from, Central Asia, for example. And that's definitely, I don't know, I honestly, my gut is that these call signs get shifted around so much in this like kind of bit hacking process that to have it fit to that certain distribution of call signs, it's possible. I don't want to say it until I've like definitively proven it. And that also might be one of the reasons to generate synthetic data of like the entire kind of set of call signs that are out there, and then like kind of add that into the training set so that in case it does have weaker performance, it would do it. But yeah, it's hard to crowdsource. Nobody really takes like gigabytes of WAV files of it. I mean, it could do it. It's just something I haven't done yet. Yeah, maybe this guy right here.
Yeah. Here.
Hey.
Hey. Yeah. Roaster this.
Yes.
Indeed. Yeah, so little bit of a different tack. It sounds to me like to get some training data, real training data, you need to arrange a special event.
Yes.
With 300 people or so to record their sessions for a couple of hours.
Yeah, that would be ideal. I think one thing that I'm most interested in, and this goes to the training data thing, is not necessarily about the different call signs, but what about top band? Like, where I got recently the opportunity to actually go contesting and sit and listen to like 80 and 160 meter at like 3 a.m. at night and like voice trying to pick up call signs, and you can hear the like lightning, like the pops like far away. It has like actually a different kind of noise background than like 10 meters or 20 meters due to just kind of like actual physics that are creating that noise. And so that's where I feel like you're going away from like non-Gaussian. I'd want to get like a 160 meter test set. And the other thing that I would want to get is it's the same thing that happens on sideband. Like when you get on voice and you call up like Robin's because it's going through the aurora, and that same thing happens to FT8 signals, and it causes them to like smear out, and they can kind of like shift around. And then there's also that like fading stuff. So getting like auroral signals would be really cool. Although there are ways to simulate that, and in the original kind of FT8 paper, the authors kind of go through to create a simulation. I even updated that as well myself. So That's what
Oh.
that'd be the coolest to do. Yeah.
Set up a special
Yeah.
event and offer certificates to
Yeah. Oh,
people.
great idea.
And
Yes.
and you'll get several hundred folks. Sign me up for the top fan.
Yeah. Yeah.
First,
Yeah.
thank you.
I'm going to offer you something first. So I'm doing a project with end-to-end machine learning decode of CW. And for that, I have built what I believe is the most advanced synthetic data generator for HF. So if you want to pull the QSB and the noise portion of that and overlay that onto FT8, it would probably
That'd be
be
awesome.
very useful. I've also built tooling to record effectively infinite real HF signals on every band distributed across the world simultaneously.
Yep. Yeah,
And
actually, we talked about this, like, it was like at field day or whatever. I was like, yeah, I'm going to try and write this like decoder thing, so we can make a skimmer. And I remember we had a long conversation about it. It's like, well, it took a while, but it's getting there.
I have the tools. They're at home running right now. I have 2 GPUs warm up my garage right now, training the model, and the machine is downloading at like, I don't know, a megabyte a second of data from a whole bunch of poor WebSDR hosts.
Yeah.
Oh,
that's really interesting. Okay.
yeah,
Oh,
but I have the tooling for you. Yes, I have a worldwide all band data set.
Okay, that would be really interesting. You've got
so I'd be happy to share those tools narrowly, because if I share them with this broad group, we're probably going to get banned from WebSDR as a club.
Yep.
But my question was, have you considered just an end-to-end machine here? Because back in math said wouldn't even be okay.
Oh, I mean, all right. So this is getting into some inside baseball. Okay, so there are papers which I've read, and I even like corresponded with one of the authors to, like, a neural network. This, you can kind of put in like somewhat arbitrary computation to these things, and you could even take the like LDPC code, which is essentially defining a relationship between the payload bits and the parity bits, and try to use the LDPC code in the demodulation step itself.
Yeah.
And so we're called code aware.
There's a really long conversation I have here.
Yeah.
Right? But
so I've thought of it. It's out there. I think what I really want to do is get the whole thing threaded through and like be like, all right, can I decode more?
I want to make a Warren Buffett style bet here that all your hard work could be replaced with an end-to-end model with no context whatsoever.
Will it run without a GPU? I think that's like, I don't know. It depends, will it?
It will.
Okay. We'll see. Someday. I'm still in
Okay.
a few.
Andy had a question. I think we're probably going to have to wrap it up, folks.
It's a short question. Do you have to have a very modern multi-processing parallel processing machine to do all these improvements?
No. So that's part of the thing. Some of these decoders are just straight up faster. So even WSJTX and MSHV and these other kind of applications that you use, like, you don't need a mega powerful computer to do it. There's just a setting that you kind of control, like how much on decoding. And so you set that at like a little lower level, and yes, you're going to lose some of the decodes, but it's not going to be so bad. Here, the goal would be, for the same computer, can you run more intense decoding because it's more efficient? And so it would apply in that case if we, put it into the real thing. And that's kind of the same comment like on these small portable computers where you don't have a ton of compute, all of that will kind of translate. Yeah.
Thank you so much. Yeah, for sure. One of the things about this topic is I would have never known, because, digital isn't my thing, but there were so many layers to this, which is really interesting. But your passion that you have when you talk about this is like pretty cool, actually.
Yeah.
And when you come up with a possibility of trying an experience, you display this like, ooh, I gotta try this.
Yeah.
So, and that kind of passion makes people, energetic to learn. So thank you for being here. And I'm sure that if those slides are available, let me know, because they'll probably want to go back and review them.
Yeah. Great. Thank you, everybody.
Yeah, thank you, David. That was very cool. I'm assuming next month is probably a little early, but maybe you can help supercharge our FT8 station next year at Field Day. That would that would be okay.